Okay, everyone. We are going to now take what we have learned so far in this unit and apply it to some real-world applications. Now, most of the problems that we see from our homework in our textbook for this section, we actually are going to use technology or Desmos to help us solve it. Even though we've learned different types of factoring, when we get into cubic and quartic functions, okay, there's other types or other ways of factoring that we just don't get into in this course. And hence, we often need to use technology to solve some of the questions or answer some of the questions that pertain to these word problems and polynomial functions. Okay, so even though we've learned how to factor, we mostly have concentrated on factoring quadratic equations or expressions. Okay, and we've also learned how to common factor. So, we can certainly apply any sort of common factoring that we've done. As you'll see in one of the questions I do here below, I'll be doing that. So even though we have a cubic function, I can common factor it and then actually factor it as a simple trinomial afterwards. So it is possible to factor some of these questions, but a lot of them we're not able to factor them, okay? And so we need some other way to be able to solve them. And for this particular course, that using technology is going to be the way that we solve them and not algebraically, okay? But you'll see in these two questions that I'm going to go through as part of this lesson, I'm going to take you through both. The fact that we can answer all the questions algebraically if we wanted, and then I'm also going to pull up the graph on Desmos and show you how you can also get your answers from the graph. Okay, so I am going to show you both, but for the most part in our homework, it's going to be from Desmos. Okay, so let's start by just refreshing or knowing how to evaluate a simple question like this. The following polynomial function, f at x equals x cubed plus 2x squared minus 3x plus 1. So we're evaluating for x equals negative 3. And all you need to do here, okay, is simply substitute negative 3, okay, for x. Okay, so let's find f at negative 3. And whenever we see an x, we are going to substitute it with a negative 3 in brackets. Okay, always, when you're substituting for values, you always put them in brackets. Plus 2 times negative 3 squared minus 3 times negative 3. Okay, so negative 3 cubed is negative 27. Plus, and I'll write out all my steps. So I'll keep the 2 where it is. I'm not going to do any multiplying yet. I'm just going to figure out negative 3 squared, which is positive 9. So it's 2 times positive 9. Okay, and I'll just rewrite the rest so that I do all my multiplication in the same line. But you definitely don't need to do that. So 2 times 9 is 18. Okay, there's 2 ways you can interpret this. You can do this as negative 3 times negative 3 becomes plus 9. Or I'll kind of do it the longer way. I'll bring down my minus sign and then do 3 times negative 3, which is negative 9. And notice I put that in brackets because I saw that there was a minus sign ahead of it, which means I need to distinguish between those two, the minus and the negative there. Okay, now, you should recognize, remember I said that you could have just handled this as negative 3 times negative 3 is plus 9. Well, you can see why this is also going to work. The negative and the minus sign there will become plus. So you end up with negative 27 plus 18 plus 9. Okay, and what do you get there? You actually get that f at negative 3 is equal to 0. Okay, so it's equal to 0. Now, let's get into, that's just one of the examples, that you need to do or just have knowledge of. So I wanted to put one of those in there because you'll see that a lot of the questions now that you'll get in this unit will require you to substitute numbers into your equation and then solve your equation accordingly. Okay, but let's get into an example. Like I said, we're going to solve this kind of manually, and then I'm going to show you how you would solve it using a graph, or at least answer some of these questions using a graph. Okay, so a swimming pool is being drained. The volume V at T in liters of water remaining in the pool after T hours can be modeled by the following function. Okay, so V is volume, T is time in hours. So we have 0.48 times 48 minus T all cubed. Okay. All right. So I'd say that the first thing that you need to do is start thinking about this equation. Okay. And maybe start thinking about what the sketch of the graph might look like. Okay. What it might look like. So it's a cubic function. So I'm just going to make note that it's a cubic function. And how do I know it's a cubic function? Okay, well, there's the exponent 3. This is in factored form, actually, and that's another thing that I should make note of, that this equation is in factored form. So I'm just writing down things that I know, okay? So it's in factored form. How do you know it's in factored form? Well, there is this situation where we have a number times a bracket or a factor, and then that is raised to a power, okay? So I know that this is in factored form. It's certainly not in standard form, right? Standard form would look something like f at x equals a, x squared plus bx plus c. And it certainly doesn't look like that, okay? So what else do I know from here? Well, I know that my a value, okay, so my a value is currently showing to be positive. Okay, that's something to note, although let's see once we graph it what that ends up looking like. Okay, but let's just leave it at that. We've got a cubic function. It's in factored form, which means we can find x-intercepts if we need to. Okay, so we can find the x-intercepts. Okay. And we'll do that in this question, actually. It'll come in handy for us to be able to do that. All right, so let's answer. How much water was in the swimming pool initially? Okay, so ask yourself, what do I need to obviously you need to substitute something in to find out what the initial volume was. Okay, now remember, your initial volume, it's going to be something like this. Let's say this curve looks something like this. I don't know, something along these lines. Okay, it's a cubic function. So the initial volume is wherever the y-intercept is. So we are looking for the y-intercept. That's what we're looking for in this question. All right, so for the y-intercept, what is x always equal? X is always 0, or in this case we have t, okay? T is always 0 for any y-intercept, okay? So we're going to sub in 0. So we're going to go like this. We're going to go v at 0 is equal to 0.48 times 48 minus, now replace wherever you see a t, replace it with a 0. Okay, and now solve. Do your brackets first. Okay. Now, obviously, do your exponents next. So do 48 cubed. Okay. And it is going to be, keep your 0.48 in the front, and it ends up being 110592. That's 48 cubed, and then multiply it by 0.48. So you're going to end up with a odd decimal here of 53,084 liters. So that's the initial volume of water in this pool. That's V at 0. When time is 0, that's how much water is in the pool. Because remember, this pool is draining. Okay, so this pool is draining. So realistically, this sketch might look more something like, now that I can see where my y-intercept is, it's going to be up in like the 50,000 area, right? So it might do something like this. It might come down and do something like that. You know, this negative side of it is irrelevant to us. We're only looking, of course, time doesn't go negative. Time only stays positive. So we're starting at time 0 there, right? So this other half of the curve, although mathematically it exists, it will not exist for us. Okay, but again, this is just a quick sketch. It actually doesn't open that way, but I just wanted to do just a quick drawing. Okay, so we don't really need that there. Okay, so how much water is in the pool after 5 hours? How much water is in the pool after 5 hours? No problem. This is just like the question here. Simply sub in 5 for t. So we're going to find v at 5 is equal to 0.48 times 48 minus 5, because we replaced t with 5, cubed. So we end up with 43 cubed there. And work out that math, do your exponents first, and your final answer there for v at 5 is equal to 38,163 liters of water. Okay, so that's after 5 hours of draining this pool. That's how many liters you'd have. Now comes the trickier part here. So after how many hours was the pool empty? After how many hours was the pool empty? So this is what I mean where a sketch comes in handy. Okay. Okay, so let's draw a nicer sketch here of what's happening, right? So we have V and T here, and we know that this is a cubic function. And now that we've done a few of our lessons, we know that it's in factored form and that the x-intercept here is going to be a third order intercept. Okay, because our factor has a to the power of 3 with it, okay, or raised to the power of 3, we know that it's going to be a third degree, okay, a third order, intercept. And so what does a third order intercept through the x-axis look like? It's going to look like one of these little dog legs through the x-axis. But I mean, it's on a little bit of an angle, so it is still only going through the 1 point. But if we know that our y-intercept is at 50,000, right? So we know that our curve is going to do something like come down from here, okay? And then when it crosses the x-axis, it's going to do one of these little dog legs, okay? Now, if we want to find out how many hours the pool, or after how many hours was the pool empty, we really, if time starts here at 0, this is the value we are looking for. So what they're really asking us, right? This is going to be how long it took for it to empty down to 0 volume. So if we are really analyzing this question here, what we're really looking for is our x-intercepts or x-intercept. Okay? That is what we are looking for here. That's what they're asking for. And then once we have that other x-intercept, we know that that's how long it took to be emptied. Okay? So let's take a look at how to find our x-intercept. Well, let's see. If v at t equals 0.48, 48 minus t cubed. Okay, all you need to do is set the left equal to 0, right? Because y has to equal 0, or in this case, v has to equal 0. And then ask yourself, okay, what value of 0 or what value of t will provide me with the right side of the equation equaling 0? And the little shortcut to do that is simply set your bracket here equal to 0. Because if this bracket equals 0, then the whole right side will equal 0. right? And I'll show you why in a second. But let's do 48 minus t equals 0, okay? And just over here, I'll just do that. I'll bring the minus t over to that side, and we get 48 equals t, which makes perfect sense, right? 48 minus 48 would equal 0, okay? In which case then 0 cubed is still 0, and then 0 times 0.48 is still 0. So you get the whole right side equal to 0 if t is 48, okay? So that value there is 48 hours. So then, of course, write your therefore statement after how many hours was the pool empty? After 48 hours. Okay? How can you determine the domain of the function by simply examining the function? Okay, well, I just drew a sketch here. So let's actually go into Desmos and I'll actually draw the graph. Okay, and we'll examine the function from there, but then we'll also take a look at the equation and then we'll look at how we can answer this question. So let's go into Desmos and let's plot, and I'll just use y equals 0.48, open a bracket, 48 minus x, close my bracket, raised to the power of 3. Now, you're not going to see anything here. Okay, why? Because clearly my window here needs to be zoomed out a lot. How much does it need to be zoomed out? Okay, well, let's go back to our question. Look at the value of liters we're at when time is 0. Okay, when time is 0. When time is 0, we're at 53,000 liters. So our y-axis has to at least be at 53,000. Let's go up to like maybe 60,000. Okay, and there you can see that the curve will start to pop up, and we can go even more than that. Let's go maybe even 80,000. Okay, but what about our x-axis? Well, we just found out that it'll take exactly 48 hours for the water to run out. So our x-axis at least has to go up to 48. Let's go to 50, or let's go even more than that. We can even go 60, 70, so we can see beyond it. Let's go to 70. Okay? And there you have it. So if we were to find our, there is our x-intercept. It's at 48,0. There's that little dog leg I was telling you about. There's our y-intercept. Okay? Both important points there. So the only part of this graph that we're concerned with, okay, is from 0 to 48, because we know that the other values don't exist in real life. Like the left of this graph here, right, -10 for x, I mean, you can't have negative time, and you also can't have negative volume. So all you're really dealing with is this section from 0 to 48, and that is it, just from 0 to 48, okay? So you can see that, again, let's analyze this a little bit, that the pool empties pretty quickly to start if you're to look at where our y-intercept is starting from here. So it empties pretty quick to start. You can see it's pretty steep, but then it kind of levels off as the pool drains more and more, okay? Which makes sense. It'll start to go slower as time goes, as there's less water in the pool, okay? It'll start to drain slower to the point where then it gets down to nothing. Okay, so there's our graph, okay? And you can see that it kind of matched my rough, although my sketch was pretty ugly, but it kind of matched it. So if we go back and we try to answer this question now, how can you determine the domain of the function by simply examining the function? Okay, so by looking at the equation, okay, how can we find the domain for this particular question? Okay, well, what we did was we found the x-intercept. In this case, there was only one x-intercept. Okay, so find x-intercept or x-intercepts, plural. Okay, And secondly, I would say draw as best as you can a rough sketch of the function. Now, this obviously, in order to do all this, okay, in order to do this, the function has to be given to us in factored form. So function must be in factored form. Okay? And if we're able to do that, if we're able to draw a sketch like we did above, and if we're able to find the x-intercepts because it's given to us in factored form, we can figure out the domain here. And by the way, our domain for this question, okay, we're going to use the letter t instead of x because we're dealing with time. T is an element of any real number, but t must be greater than or equal to 0, but also less than or equal to 48. Okay, there is our domain for this question. Okay, moving on. Okay, so example 3. A marine biologist is testing a new underwater probe. The probe is catapulted from the ship into the air, descends underwater to a predetermined depth, then returns to the surface where it can be collected. The function that models the probe's path is there, where x is time measured in seconds. Okay, so again, let's analyze this a little bit. So the probe is catapulted from the ship into the air, okay, descends underwater to a predetermined depth, then returns to the surface. So if I were to just quickly draw something, it gets catapulted from a ship, goes underwater, and then returns to the surface, kind of thing. Okay? Well, we have here a cubic function. I'm just going to start writing down some things that I know. I have a cubic function. Its leading sign of the coefficient here is positive. So positive leading sign. Okay, which means the direction will be going up and to the right. Okay, so I know that. I'm just thinking of, it helps me analyze the question if I just start to write down everything that I know about it. Okay, so again, actually, question A actually asks for the type of function that we have. Okay, and we have a cubic function. Okay, because of the degree 3. Okay, which finite differences will be constant for this function? Well, it is definitely going to be the third differences. Okay, remember we did this in the last lesson or a few lessons ago. The third differences will be constant if it is a cubic function. Okay, describe the end behavior of this function assuming there are no restrictions on the domain. So let's say that this is a theoretical equation. It's not a real life application where no negatives are considered. Okay, what will the end behaviors be? Well, like I said here, our sketch of the graph is going to look something like this, where it goes underwater. So it's essentially going to be going like this. Okay, this is the theoretical sketch of what it will look like. It's going to be going up and to the right. It's a cubic function, so it's going to have at most 2 x-intercepts there, and we will have 2 x-intercepts here. Okay, so here's our end behaviors, here and here. So let's describe what's going on. Okay, let's describe what's going on. Here's our x, here's our y. Okay, so as x approaches positive infinity, what is happening to y? So as x goes to positive infinity, y, this curve is also moving up, so y is also approaching positive infinity. And as x approaches negative infinity, y is going to also approach in the same way as x goes this way. Okay, our graph is going downwards, so y is also approaching negative infinity. Okay, so fairly straightforward so far. Okay, what are the restrictions on the domain of this function? What are the restrictions? Okay, so now, like I said above in this question here, where the question said, how can you determine the domain of the function by simply examining the function? Well, you have to be able to find the x-intercepts and draw a rough sketch of the function. Okay, those will help us. However, that's only if you're in factored form. Are we in factored form with this equation? No. And this is why most of the questions in the homework, you'll be using technology to simply graph it. Okay, and I'll go through that after I finish doing the algebraic way, because we actually now can factor this and put this into factored form. Okay, we can do that. Okay, so I'm going to do that, but not all of the questions in the homework. In fact, most you cannot factor. You have to use graphing technology. So right now we'll factor it, and then we'll go through the graph on Desmos and pretend as if it wasn't factorable and see how to solve it just by looking at the graph. Okay, but I am going to factor it right now. So we've got 15, and I'm just going to factor it down here. We've got f at x is equal to 15x cubed, okay, minus 195x squared plus 450x. So I told you that we can factor this, okay? So let's start. Remember, always look to common factor first. Let's pull out a 15x, which is common, because 15 goes into each one of these numbers. And since there's an x cubed there, x squared, and x there, what's common is just one of those x's, or x to the power of 1. So we can pull that out. So let's open up a bracket. Let's divide by 15x for each term. Okay, what are we left with? Well, we are left with 15x cubed divided by 15x is simply just x squared. Okay, now 195 divided by 15 is what? Okay, should have gotten, and bring down your minus sign, should have gotten minus 13. And the x's, we have x squared divided by x, which means we're just left with an x there. Subtract the exponents. And then 450 divided by 15, bring down your plus sign, is 30. And the x's cancel each other out there. So we have this so far as our factored form, but we're not done yet. We see that there's now a trinomial inside my brackets that I can further factor, right? So even though I have the 15x, I can't do anything with that right now, but I actually can factor this simple trinomial in my brackets if I find two numbers that multiply to 30 and add to negative 13. Okay, I know what you're thinking, 15 and 2, but you won't be able to work the positive and negatives with 15 and 2. But if we do negative 10 times negative 3, that equals positive 30. Negative 10 plus negative 3 is negative 13. So negative 10 and negative 3 are my two factors there. So I'm going to just write it as x minus 10, x minus 3. And there you have our fully factored version. Okay? Fully factored version. So we are now going to be able to draw a quick sketch here, okay, of what's going on. So here's our equation in factored form. Okay? Which means that there are intercepts, 3 of them, at x equals 0, x equals 10, and x equals 3. Okay, so now I'm going to draw a quick sketch. X-intercept at 0, x-intercept at 3, and x-intercept at 10. Okay, so what's happening here? Remember, I said that the graph has to go up and to the right. because it's a positive leading coefficient. So it gets to here. At this point, it gets catapulted from the ship. It drops back down, crosses the x-axis, goes underwater, and eventually ends up back above or at the surface of the water. And now theoretically this will continue, but for our question in real life, we're only concerned with from here to here. This is all that matters for us. So what are the restrictions? What is the domain here? What do our x values have to be for this particular question? Okay. X has to be between 0 and 10, and it can equal 0 and 10 as well. Okay. All the other values of x don't matter because this is a real world problem. We don't deal with the theoretical stuff of what actually happens theoretically. We're only concerned with what is happening with the real life stuff. Okay, so now let's say this is a homework question and you cannot factor the equation. Okay, so it's not factorable. How can you answer this? Very easy, and in fact, it's a lot easier than what we had to do. Okay, you just take your original equation here and plot it and look at the graph and see which x values make sense. Okay, so let's go back into Desmos and I will delete what's there, go home. Okay, and let's go y equals 15x to the power of 3 minus 195x, okay, squared, and then plus 450x. You can see that I can't see everything that's going on here, not even close. Okay, so we need to figure out what we need to make our window here. Well, first off, on our x-axis, I want to at least go from, let's say, 0 to 20, just so we can see a little bit beyond 10. So let's go 20 here. And let's go maybe just -2 there. Okay. But how do I know where to go for my y? And I guess the best thing I can tell you to do is just find the y-intercept. Sub in 0 for x. Okay. You want to at least be able to see where the y-intercept is, right? Sub in 0 for x and see what you get. Okay, so we've got 0 cubed. Oh, 1 second. I think I wrote down the equation wrong. Nope, it's all good. Okay, so let's see here. Let's start playing around with these values. Sorry, our y-intercept is at 0, so that's not going to really help us. It's not going to help us with the maximum of this curve. Okay, so let's just start playing around with some different values and see if we can see this curve a little bit better. So let's go to our gear. On our y-axis, let's go to 100. Okay, still no good. Let's go higher. I want to be able to see that maximum there. Let's go to 500. Okay, that's not bad. Maybe we can go a little bit lower and go to 400, right? And I just picked these numbers kind of out of a hat. Okay, there it is. And wow, it really goes underwater quite a bit. Okay, really goes underwater there. Okay, so again, here's what we're concerned with. So it gets catapulted at 0, gets catapulted up into the air. It drops back down, it goes underwater. I'm not too concerned about how far down underwater it goes. Okay, and then it pops back up at 10 after a time of 10 there. Okay, and I believe that was it 10 seconds? Yeah, where x is time measured in seconds. Okay, so looking at that graph, you can see that the only x values that are relevant to us are the ones from 0 to 10. So from when it gets catapulted, goes up, goes down into the water, okay, and then comes back up at 10, okay, that is all we are concerned with. I'm not concerned with anything that goes up beyond 10 there, okay, because with this situation, it would just stay on top of the surface of the water, even though mathematically the curve would continue, okay, in real life, I mean, it would just stop at the surface there. So from this, you can tell that the only x values that matter to us and what the domain is from 0 to 10. Okay, so from 0 to 10. So basically my advice to you is to graph this out on Desmos for the technology questions and really just make sense of the question to figure out what part of the curve is relevant to the question. From there, you'll be able to tell what the domain is. Okay, let's go back and finish this off. Determine the height of the probe 2 seconds after takeoff, no problem. And you can use either version of the equation here, our factored form or the standard form. Let's use the standard form just in case, you never know, you can make a mistake with the factored form and then you're plugging a number in into a wrong formula. So let's use the original. Sorry, let's do f at 2 is equal to 15, 2 cubed, minus 195 times 2 squared, plus 450 times 2. Okay, and then you go about and you figure out what all this would be, of course. And so 2 cubed is 8. So I'll just do all my steps here. I'll do 15 times 8 minus 195 times 4 plus 450 times 2. Okay, well, 15 times 8 is 120 minus 195 times 4 is 780, and then plus 900. Final answer for f at 2, okay, it is 120 minus 780 plus 900. We are at a total of 240, and I believe we are in, okay, didn't say if we're in meters. Let's assume that we're in meters. 240 meters into the air, okay, after just 2 seconds. So that's still probably part of the catapulting part. We're at 240. And we can verify that on our graph, actually, very easily. If I now graph the line x equals 2, okay, you can see that it'll draw a line, a vertical line going through x equals 2, and it'll show me the point of intersection and what y value it matches up with. So it matches up with 240 there. Okay, so this is where it would be along its path. It would have gone up and then come back down. After 2 seconds, it would have just started to come back down. Okay, so hopefully this was fairly clear to you. Again, to recap, that for some of the questions in the homework, I say that you can do it by hand, and then some of the questions, most of the questions, you do have to use technology because you won't be able to factor it. I've shown you how to do both, okay? Please try all the questions. There's quite a few of them, okay? And what I love about using technology is it really helps you visualize what's going on. So make note of that, and hopefully you learn from that.